Hey everyone, and welcome to this set of numerical practice problems. And the topic that we'll cover today is about ordinary differential equations. We will have two questions. The first one will be about initial value problem, and the second one will be about the boundary value problem. So let's start with the first one. So here it says that for the following equation, which is the dy by dt equal to sine of t plus e of t, using the Euler methods first, and then the modified Euler method, and finally the Rank-Coota methods, find y at 1.5 using the following condition. This is an initial value problem, so we know that y of 0 is basically equal to 1, and your h, your delta x, or your increment is 0.5. So we know y at 0, the initial conditions. We want to find y at 1.5, and this is the increment that we'll be using. So we need to find y at 0.5, 1, and 1.5. So this is the formula for the Euler methods, that the y of the current iteration is equal to y of the previous iteration time plus h. H is your increment here, times the function. And here is our function. This is our function, sine t and plus e of t. So we will start with y at 0.5. So this is the next point. The existing point is basically y of 0. And this is equal to the previous one, which is y of 0 plus h. H is our 0.5 times the function at tn, which is the previous time, which is basically 0, and your y1, which is 1. Y at 0 is equal to 1. So this will equal to 1 y of 0 plus 0.5 times, now we evaluate the function at 0 and 1, so it would be like t is 0, so this would be like sine of 0 plus e to the power of 0, and this will give me 1 plus 0.5 times 1, and this will give me 1.5. Then we go for y1, which is equal to y of 0.5, the previous value that we just calculated, plus 0.5 times your sine at 0.5, because this is now your new t, plus e to the power of 0.5, and this will give me 2.564, and so on and so forth. And here is the total answer. So we start from x 0, the initial condition is basically 1, and your function, this one, is equal to 1. Then we go to 0.5, and your y is 1.5. This is the answer that we have. And then at 1, and finally at 1.5. That is my answer. This is the y, the function of the y at 1.5 is equal to 4.34395. So that is the Euler method. So now let's move on and go for the modified Euler method. So which is basically, it's a modified function from this one, from the Euler methods. So here we will have y star like an intermediate step, and the y star is basically what we have here. This is the y. This is the output of the Euler method, is the intermediate step here. So the y star at the 0.5 will be equal to exactly this value, the 1.5. This is exactly the y star, equal to 1.5. Then the y itself at 0.5 would equal to the y at 0 plus h, which is 0.5, the function at 0 and 1 plus the function star, which is for the current one, which is at 0.5, and y at y star, which is the 1.5, divided by 2. So this will equal to y at 0 plus 0.5 times the function at 0 and 1. We substitute there. This will be equal to 1 plus the function at 0.5 and 1.5. So this is your t basically. We substitute t equal to 0.5. This will give you 2.128147. Everything divided by 2, and this will give you 2.5. Your yn, sorry, this will be 1.782037. And then we go to y star at 1, and so on and so forth. And here is the answer. So you look here. So we have, this is your x. Okay, so this is your 0.511.5. You find basically the intermediate step, which is nothing but here. This is you see the output here is matching the output of the intermediate step. They are exactly the same. So this step is the same as the Euler methods. And then we find the functions at both at the initial or the previous t and at the current t. The function is only a function of t. Okay, so here you can see that the t here is 0, the t here is 0.5. And then we can find y of n here. Okay, so we start with 1.78, then we go to 3.204, and finally the final answer is 5.463746. So that is the modified Euler method. Now let's go to the third technique, which is basically the Rank-Coota. Now here, this is the formula for that. This is the formula for the Rank-Coota. So we need to find K1, K2, K3, and K4. So your K1 is equal to H, which is basically your 0.5, and the function at Tn here, which is basically 0, which is equal to the function sine of 0 plus e to the power of 0, and this will give you 0.5. Your K2 is equal to 0.5 times Tn. So now the time that you will have here is Tn plus 1/2 h. So this will be sine 0 plus 1/2 times 0.5. So this is the time here. So this is the time, Tn plus 1/2 h, and then plus e to the power of the same thing, the same time, which is basically 0 plus 1/2 times 1/2, or 0.5. And your K2 will be equal to 0.7657. Your K3, now we'll see K3 and K2 they are basically similar to each other. So this will be equal to, now because we don't have the y here as in the function, so we get exactly the same value, which 0.5 sine of 0 plus 1/2 times 1/2 plus e 0 plus 1/2 times 1/2, and this will give me a K3 equal to, again, 0.7657. And finally, we'll want to find K4, which is equal to 0.5, the function at t plus h. Now t here is 0, h is 0.5. So this will be basically equal to sine 0 plus 0.5 plus e to the power of 0 plus 0.5, and this will give me 1.064. Finally, my y now at 0.5 will use this formula, which is equal to y at 0 plus 1 over 6 times 0.5 k1 plus 0.7657 times 2 here, plus again 2 times 0.7657 plus K4, which is 1.064. And of course, Y0 is basically 1. So we can find here Y at basically 1.5, which is 1.771. Okay. And here you can see in this table all the answers. Now this is at 1 and this is at 1.5. And here are the values of K1, K2, K3 and K4 and the functions calculated at these values. So that is basically how we can use the boundary value problem using the 3 different techniques. Now let's have a different problem, which is basically our previous one was the initial value problem. This is now the boundary value problem. Okay, so here we have a second derivative, second order differential equation. Okay, and we know the boundary at 0 and the boundary at 1. So we have the boundaries. Okay, and then we have the h.2. So we have from 0, 0.2, 0.4, 0.6, 0.8, and 1. And we need to find the function at 0.2, 0.4, 0.6, and 0.8. So we know the two extreme boundaries. We know y at 0, which is here. I know y at 1, which is there. And I want to find in between. So we have basically four unknowns. And then we'll compare the exact answer if this is the answer for this second order differential equation. How to find that. So first, let's set our unknowns basically. Sorry. So here is basically our I. So we start from 0 and end up at 5. So we have basically 6 different values. So we know the first one and the last one, and the intermediate one, we don't know them. Now your x, this is just a counter, 0, 1, 2, 3, 4, but x starts from 0, which is a known value to us. So we know the value is equal to minus 1, end up at 1, x1, and we know the value at this is equal to 0. So we know the two extremes. What we don't know is what is the function of y at 0.2, 0.4, 0.6, 0.8. So for these x values, what are the values of y? We don't basically know. And here we want basically to solve or to create 4 equations with 4 unknowns to solve for this. So the first thing we need to do, basically, we want to replace the first derivative and the second derivative with the definitions of the derivative using the numerical method formula. So y prime, we use the forward divided difference is equal to yi plus 1 minus yi over h. And the second derivative is yi plus 1 minus 2yi plus yi minus 1 over h squared. So now we will have here y double prime and y prime. So we'll come and change that as we will see here. So that is the original differential equation. Now I will change this y prime to this, and this y prime to the definition of the first derivative. The rest stays the same. With the now, since we want to do or to find the solution at certain I, okay, so this will be I, the value x will be all at I, at the current increment, okay? But the formula will have I plus 1, I, and I minus 1, as you see here in the y formulas. Okay, now we need to create basically equations. We need to create 4 equations. So we start with I is equal to 1. So this is my first equation, I equal to 1. So basically here this becomes y. So let me, this is the previous table. So let me have this here. So this is y, I1, so this is I2 minus 2y1 plus y0 divided by h square, which is 0.2 square, plus the current xi is 0.2. This is your I equal to 1. We are at this stage here. Okay, plus 1, yi plus 1, which is y2 minus y1 divided by 0.2 equal to 1 minus 0.2 square e to the minus of 0.2. Now, y at 0, we know the value. Y at 0 is equal to minus 1. So this will be minus 1. So now if we just collect terms, simplify the equation, we get the first equation, which is equal to 31 y2 minus 58 y1 is equal to 25.786. That is my first equation. Now we need to do the same thing, create second, third, and fourth equation. So now we go for y, for I equal to 2. So basically here we'll have substitute here, y3 minus 2 y2 plus y1 divided by 0.2 square plus 0.2 plus 1 y of 3 minus y2 over 0.2 minus 2 times y2 equal to 1 minus, now xi is equal to 0.4. So minus 0.4 square times e to the power of minus 0.4. Now let's arrange terms here. So we'll get 32 y cubed minus 59 y squared plus 25 y1 is equal to 0.563, and this is my second equation. Now we go for I equal to 3. Okay, so we will have substitute here. We'll have y 3 plus 1, which is 4, minus 2y3 plus y2 divided by 0.2 square plus your xi, sorry, here, this should be not 0.2, this should be 0.4. Okay, so it's not 0.2, it's 0.4. And this is here 0.6 plus 1, y4 minus y3 divided by 0.2. Okay, h doesn't change, but x, the one is changing. Okay, minus 2y3 is equal to 1 minus 0.6 square e to the power of minus 0.6. Now, when we basically try to simplify the equation, we will get the third equation, which is 33 y to the power 4 minus 60 y3 plus 25 y2 is equal to 0.351, and that is my third equation. Now let's go for the last equation. I is equal to 4. Now here y5 minus 2y4 plus y3 divided by 0.2 square plus xi is 0.8. So this is 0.8 plus 1. And this is basically y5 minus y4 divided by your h, which is the 0.2 minus 2y3 is equal to 1 minus your x here is basically 0.8 square e to the minus 0.8. Now let's basically try to simplify the equations. Minus 61 y to the power 4 plus 25 y 3 equal to 0.1618. Now, as you know, y5 is a given value, it's a known value, and it's equal to 0. Okay, so now this is our fourth equation. Now we have 4 different equations. I will put them in a matrix form. So these are my 4 equations, and I need to solve. Now you can use any technique like Gauss elimination, for example, and solve for that. And these will be the values of y1, y2, y3, and y4. This is the y at 0.2, 0.4, 0.6, and 0.8. And then now these are the x value. This is the estimated value of the y's that we have here. And then this is the exact value from the solution that was given to you. And then we can find the absolute error, and we can find the percentage relative error. So that's how we can handle a boundary value problem. So hopefully with these 2 examples, we have an idea now how to handle an initial value problem and a boundary value problem.